Welcome to Chapter 3 of the RAG Introduction series. In this chapter, we'll explore advanced techniques that significantly improve RAG system quality. You'll learn about query optimization through decomposition and HIDE, re-ranking with cross-encoders and MMR, hybrid search combining keywords and vectors, and context compression for efficiency. These techniques can transform a basic RAG system into a production-grade solution. Query decomposition breaks complex questions into simpler subqueries. Consider the question, compare AI market size in 2023 and 2024 with future forecasts. A single search might miss information. Decomposition splits this into three searches: 2023 market size, 2024 market size, and future forecasts. Each subquery retrieves targeted results, which are then merged with duplicate removal. This technique handles multifaceted questions better than single queries and ensures comprehensive coverage of complex topics. HIDE is a clever technique that generates a hypothetical answer before searching. Instead of embedding the question directly, you ask an LLM to write what a good answer might look like, then use that hypothetical document for similarity search. The intuition is that the hypothetical answer is more similar to actual answer documents than the question itself. For example, when searching for "How does attention work in transformers?" a generated technical explanation will match real technical documents better than the question text. You can also combine HIDE with normal search using weighted fusion. Re-ranking improves result quality through a two-stage approach. The first stage uses fast biencoders for initial retrieval, encoding query and documents separately. The second stage uses cross-encoders that encode query and document together, producing more accurate relevance scores, but at higher computational cost. The typical pattern retrieves 20 candidates quickly, then re-ranks to the top 5 with a cross-encoder. Models like MSMARCO Mini-LM are optimized for this task. This two-stage approach gives you both speed and accuracy. MMR addresses a common problem. Top search results are often redundant, containing similar information. MMR balances relevance with diversity using a simple formula. It selects documents that are relevant to the query but dissimilar to already selected documents. The lambda parameter controls this balance. High lambda prioritizes relevance, low lambda prioritizes diversity. When presenting search results to users, MMR ensures they get varied perspectives rather than the same information repeated. It's particularly valuable for research and exploration use cases. Hybrid search combines BM25 keyword matching with vector semantic search. Each approach has strengths. BM25 excels at exact term matching, names, and technical codes, while vector search handles synonyms, related concepts, and paraphrasing. By fusing both result sets with configurable weights, you get comprehensive coverage. For example, searching for ML evaluation metrics with hybrid search finds documents containing those exact terms via BM25 and documents about machine learning performance measurement via vectors. The weight parameter lets you tune the balance based on your domain. Reciprocal rank fusion, or RRF, is an elegant way to combine multiple ranked lists. The formula assigns each document a score based on its reciprocal rank in each list, then sums across lists. Documents appearing highly in multiple lists get boosted scores. The beauty of RRF is that it doesn't require score normalization. Different search systems produce scores on different scales, but ranks are always comparable. The K parameter, typically 60, controls how much position matters. RRF is simple to implement and widely used in hybrid retrieval, though the reference implementation in this chapter fuses its two result sets with normalized weighted scoring instead. Context compression addresses a practical challenge. Sending too much context to the LLM is expensive, slow, and introduces noise. Compression extracts only the query-relevant portions from retrieved documents. An LLM reads each document and pulls out sentences that directly relate to the question. In the worked example, This cuts the token count by roughly 70%, though the actual reduction depends entirely on how much of each document is relevant to the query. Two approaches exist. Extraction keeps relevant sentences verbatim, while summarization condenses the content. For cost-sensitive applications, compression is essential for maintaining quality while controlling API costs. Let's see how these techniques combine into a complete advanced pipeline. Starting with a query, decomposition splits it if complex. Hybrid search runs BM25 and vector in parallel, fusing the two result sets with normalized weighted scoring or with RRF as an alternative. Cross-encoder re-ranking selects the highest quality results. MMR ensures diversity if needed. Context compression reduces tokens before LLM generation. Each stage is optional and configurable based on your requirements. For complex queries, use decomposition. For quality-critical applications, add re-ranking. For varied results, enable MMR. And for cost control, apply compression. Let's recap Chapter 3's key techniques. Query decomposition handles complex multi-part questions by breaking them down. HIDA generates hypothetical answers for better document matching. Cross-encoder re-ranking and MMR optimize result quality and diversity. Hybrid search combines keyword and semantic search strengths. Context compression reduces cost while maintaining quality. Remember the selection guide. Use decomposition for complexity, re-ranking for accuracy, MMR for diversity, hybrid for coverage, and compression for cost control. In Chapter 4, we'll cover production deployment including system architecture, performance optimization, and monitoring.